The lecture today is going to be about debugging data science. This is a topic that I think is actually the one that distinguishes what I would call kind of experts in data science from people that know some algorithms but don't really know how to make them work on real data. And so I think it's going to be really sort of important as a set of topics. So anyway, a brief summary of what's going on here. I changed some of the upcoming lectures to fit what I hope will be a more useful set of tools and techniques you can use when you're going through this on your own. And I also want these lectures in particular to be a little bit more interactive. So please do ask questions. They're meant to be kind of an exchange of ideas. And so hopefully that will this new format for the last 3 lectures at least will work pretty well. I do want to mention also homework 6, we're having some issues with it. It was sort of a conjunction of many things happening at the same time. The auto graders we had were too big for AutoLab. They actually, because we're checking VGG, which is a large network, we couldn't upload it to AutoLab without crashing, and so they weren't working. And there's been a whole bunch of things that happened at the same time. So I see all the Piazza posts. I usually simply stay away from those and let the TAs handle that, but this is bad enough that I'm looking at them. I see the issues that are there. We will try to account for these issues somehow. I don't know how yet, because I want to resolve them all before we actually say what the policy is going to be. I'm hoping today we have the first of the two of the graders up. I'm hoping we will have the third up today. I really, really hope we will. And after that, we will do what we can to account for this. Apologies, this has gone fairly smoothly. I think some bumps, and this was a pretty big bump. So hopefully no one is too stressed about that. You only have to do 1 of the 3 or 2 of the 3 questions. So hopefully, and you can get extra credit on it. So hopefully it's a good thing rather than a bad thing. Okay, any questions about this though before I move on? Yeah.
The extra credit thing, you mentioned that you choose 2 notebooks.
Yep.
What if we do 2/3 of all?
Yeah, that's fine. It was just by total points. So 66 points is the max for 688. 33 points is the max for 388. You get half credit up to 100 for 688, half credit up to 66 for 388. Yeah. You can pick and choose however you want. Yeah, we're not gonna. It would be too much work to grade it otherwise, honestly. It also might not be reflected in the Piazza or the AutoLab grade, but it will be reflected in our tabulation of your grades. Okay, so let's jump in. One note on the first point. So this is actually a topic that I think is a really important and underserved one. So over the break, I also started trying to write up some notes on this. So there are, in addition to the slides, there are also some somewhat detailed notes to this on the web page. Those are meant to be a resource. There are working drafts. I don't send people that PDF. Send people the link if you want people to check it out, just because I'll be updating them as we go over the rest of the semester, hopefully. And so do check that out as well. It's on the website, or it should be on the website now. And you can really, these slides here are more or less just kind of a walkthrough of those notes. So let me start off by imagining a hypothetical scenario that I'm sure no one here has ever encountered. You go about defining some data science task. And for the most part, I am sort of talking about machine learning type data science tasks, like prediction tasks that you want to solve. And the reality is, a lot of times, it's not that hard to formulate some tasks you want to solve, right? I see this a lot. I mean, a lot of the projects have very well formulated problems. Says, we're going to try to predict this from that. That often is not hard to actually do. What happens, though, is you set up that task, you run some machine learning algorithm on it, and it doesn't work, right? That's a very, very common failure mode. And this happens to everyone. And what on earth do you do next is the question, right? And so I'll contrast this with kind of traditional debugging. I think for most programs, you have a pretty good idea about what to do next. If your program doesn't work, you step through it. I'll mention a little bit more detail in a second. But it kind of makes sense. But with data science problems, it's very hard to know what to do next, right? How do you actually go about trying to fix the problem that you actually are encountering? And a lot of times people kind of throw a lot of stuff at it, nothing really sticks, and they get frustrated, and it's just not a very interesting experience because you have no real way of making progress. So the quote I like to use about this, or not quote, because it's my quote, but I'll get that in a second. But what I think differentiates experts in data science from novices is not the first thing you do. It's the second thing you do when that first thing doesn't work, right? And I'm calling this, it's very hard to name and anything named after yourself. So I'm going to go ahead and see if that sticks. Unfortunate ideas, I think, has already been taken by a lot of people. So, but we'll see. I don't know if anyone's named it after themselves yet. So, all right. So let's contrast this with traditional debugging. So, and by the way, please interrupt me at any point here if you have questions. I'll pause frequently to ask these things. But I'm going to contrast this with traditional debugging of programs you write. So most of the time when you're writing a program, at least this is the way I do it. I don't know how other people debug, but this is also, by the way, how you debug like auto lab programs, though maybe with more or less success of this strategy here. You have some desired input-output pairs, right? So if my program wants to sort an array, I have an array, and then I have the output of that array being sorted. That's my desired input-output pairs. And I also have some mental model of how the algorithm should work, right? I have some sort of idea of the steps involved in the process, the different conditions that should hold each step, and whether or not, and how that will lead to the end result that I want. And that can be more or less formal, right? You can actually formalize this with preconditions and postconditions. But really, for the most part, you have some idea, right, of how the algorithm is supposed to work. And so what you do is you trace through the execution of the program, either by a debugger. You can actually use a debugger. Or if you're like me, you usually use print statements, right? You just sort of print out what the state is a bunch of times. And through that, you can see where the program's execution diverges from your mental model, right? Or it doesn't diverge from mental model, and if it diverges, then you sort of know where the program's wrong. You can fix the bug in the program, and you move on. If it does not diverge, then maybe something's wrong with your mental model, and so you can go and correct that instead, right? But that's kind of, I don't know if that's captured how other people think about debugging, but that basically captures how I think about debugging when I'm debugging a program, including a machine learning algorithm, for example, but not a machine learning problem per se. And so this is very, very different from what I'll call data science debugging, right? And so in data science debugging, as I mentioned before, it's not that hard to think about there being input-output pairs that you would like, right? I have some signal, I have Twitter tweets, and I want to predict the stock market, right? Those are well-defined input-output pairs, right? People actually tried to do this, and they claimed it worked, but it doesn't work. But where this analogy breaks down is that it's different because we don't have a mental model exactly of how, usually at least, of how the prediction should work. And usually we kind of just defer that, saying, well, there's math behind it. There's this machine learning black box. It's amazing. It's going to figure out whatever signal there is in there, extract it out, and make these beautiful predictions. And that's oftentimes the model people have in mind of machine learning if they're sort of novices to the field. Because frankly, when it's taught, you're always given examples like this, right? Where you don't actually know how the problem works. You don't know how to solve the problem, but you apply some machine learning algorithm to it, and all of a sudden, magically, out pops these answers that work really well, better than you ever could. And so that's the people's mental model of how machine learning is supposed to work. And this is really dangerous, actually, because this is not how machine learning or data science is really done in practice. And so we'll get to what you should do instead of this in a second. But before I begin, I want to mention one. Oops, one of my things got. Oh, it's like it's an animation for some reason. I don't know why. There we go. Okay. Never mind. Hang on. Realize that I didn't do one thing here. Okay, better. Okay, here's my, I had left out my outline slides. I still had that text cut off somehow, but oh well. Okay, here we go. So many of the topics that we're going to cover here today, I forget what I was going to say with that but line, but whatever. Many times we're going to cover here overlaps. If you've seen a lecture before on debugging machine learning or something like this is actually going to overlap a fair amount with it. But I think there's also a fundamental difference between just debugging machine learning and debugging data science problems. And in particular, we are going to focus. Oh, now I remember what I was going to say there. I guess I didn't save with that text in there. We are going to focus largely on debugging machine learning type applications in data science. debugging like a web scraper is pretty much like traditional debugging. I mean, you have some web page, you want to output some things. You can largely follow traditional debugging to get that. So the debugging I'm going to focus on is indeed about kind of debugging the machine learning process of the algorithms. But what I will say is that there is a slight difference here in that most of the material I've seen on debugging machine learning, and I think a great example actually is Andrew Ng's lecture on applying machine learning in practice. If you haven't seen that, I would recommend Googling that. There's a link to it in the docs that I have, or in the notes that I have. It was very influential in kind of shaping, Andrew's my advisor for my PhD, and he was very influential in that way in shaping kind of how I think about problems. But I think it also focuses only on the case, sort of the second case I'm going to bring up here, which is what you do when you believe your problem is in fact possible to solve. How do you go about fixing your algorithm to better solve it? What it often doesn't cover is the question of whether your problem you set up is impossible, which is frankly often the case in data science. So I forgot, I had the outline here. So can everyone read that? Didn't show up before, but what I'm going to do in this lecture really is go through kind of step by step the steps that I think are the way you should approach a data science problem. You won't actually approach it in this order, but when I think about debugging an algorithm or debugging a whole process of data science, it's very useful to think about how you might address each of these problems. And the first step, and this is one that I have not seen dealt with that much from a machine learning standpoint, is to determine if your problem is impossible or not. Right? Oftentimes, I guarantee you some people here have proposed problems that I believe to be impossible. If you have a problem in the stock market, for example, chances are your problem is impossible. You cannot predict, to a degree that's actually going to make you money, whether or not a stock will go up and down, at least not with the data you have available and the tools you have available in this course. Maybe you can, but you have to be a lot smarter than me to do that. So how do we know if a problem is impossible? Right? Because I sort of said there's lots of problems that we would love to be able to solve that would have all this economic value if we could solve them, but there's not necessarily any reason why we should think there's any kind of signal that can predict our desired output. I've been talking for a while now. Are there any questions before I move on? It's not as interactive as I hoped, I guess, but I guess maybe ask a question to engage a little discussion. Have people uncovered this problem in your own projects so far, just by a show of hands? You're trying to solve some problem and you think it might be impossible, but you don't quite know how to show it's impossible. Which problem were you working on that did that? Okay, disaggregation of energy. Yep.
Your example.
The stock market. Yep, it's a good one. Which prices? Rental prices? Okay. Yeah, so all these things are sort of, it would be great if we could predict the energy breakdown in homes. We were doing it on homework, but you can't always do it very accurately I've worked on this research topic a lot in my own. Doesn't always work. Stock market is infamously hard to predict, despite the number of papers you see about great ways to do this. I mean, and you probably can do it to a certain degree. I mean, there are these funds that seem to do something okay, but it's incredibly hard to do it from raw data that you're going to collect off the web, right? Rental prices, that's another very hard thing. There might just be features you just don't know about behind the data. You just don't know what influence these things. And it's unclear if there's really how accurate should you be? Is your problem as you set it up just not going to be one that you can actually predict here? So the problem here, I think, is that people are sort of endlessly optimistic about the power of machine learning, right? Because it's very hard to prove a negative. It's not really possible to say this problem definitely is impossible. For reasons I'll get to. You can always find some new source of data that will magically give you the answer of the thing you're trying to prove, right? You could find some hidden, other stock signal that when you look at that, this other stock follows, when stock A goes up, then stock B goes up the next day all the time, right? You're not going to find it, but you always could find it. It's always a possibility to find that. And so people sort of always hold out hope that the problem that they're looking at may be possible. And so what should you do if you want to know whether or not your problem is impossible? Because it's very hard to prove that just by analysis alone. So, yeah.
if people looking at the problem could not solve it, then the algorithm could not.
I think I'm going to get to that in a second, right now. Yeah. So this is something I've mentioned before in classes. This should not be a brand new idea for you, but I want to sort of highlight maybe what you can do if this thing fails as well. So as I have mentioned before in class, a very good proxy for, well, actually, I guess for possibility is don't try to think about determining if your problem is impossible or not, because that's very abstract and hard to kind of quantify. Instead, see if you can solve your problem. And when I mean you, don't mean an algorithm. I mean actually you, sitting down in front of examples that you're giving to your algorithm, and see if you're able to actually make the predictions you want your algorithm to make. Right? So that's something that sort of is a very obvious idea in some ways, but it's something that people almost never do. I almost never see that in a report, unless I'm very explicit about it. I almost never see that in a report on a machine learning problem or a machine learning topic. I never see people highlight what they have tried and whether or not they believe that they can actually go about solving this problem. And I mean this quite literally, by the way. I mean make an interface that highlights your data points. You want to visualize them in some natural way. So if you have just sort of numeric features, up to a handful of these, it's probably okay to use like a table format, like use them as a CSV file. If you have image data, just use the raw images, right? Just actually have the image, part of your thing you display. If you have free text data, just include the actual text description. Include the actual text that you are going to use. Don't compute bag of words first or anything on it, because that's already processing that makes it harder for us to understand. Just include the actual text. Audio, if you have audio, include the audio. Present the actual input the algorithm will see in a way that as closely as possible resembles what it's going to see, but in a way where you can actually interpret it. And just like a machine learning algorithm, you can refer to training data in this too. So you can have one stack of paper for all your examples, plus their label, plus a positive or negative class, and you can look through these when you're deciding about some new thing. But you also have some separate pile, which is a test pile, that says, given only what the algorithm can see, what's your prediction? And on the back of it, you have the true label, and then you see how well you can actually do on this, right? And again, I mean this quite literally. We have sort of, when I've worked on data science problems, we've literally printed out pages of examples. Here's the data the algorithm sees. Is it a true? Is this a positive example or a negative example based upon our understanding of the problem, right? And you can't peek at the answers. Obviously, you can't sort of say, oh well, this yes, this one was a positive example because I saw these features here. You can't do that. You have to commit to it before you see the actual label. Yeah.
So that's easier to do when it's a classification.
Yeah.
When it's regression, how do you define I can make a good prediction?
Yeah, great. So I actually don't have this in the slides. I have a paragraph on this in the notes online. So regression is a trickier one because humans are really bad at predicting in a continuum. Right? We're sort of very bad. Same with probability, right? We're really bad at kind of saying there's a 0.8%, not percent, but it's a 0.8 probability of this event happening, 0.2 of this one happening. We just have very little sense of what that actually means, even when we study probability for a living. With regression, there's a few things you can do. So the first thing you can do is threshold it and convert it to a classification problem where you're just trying to predict is this over or under a certain threshold. What you can also do is a comparative kind of ranking-based analysis where you actually just give two examples at once, and your goal is not to say what's the actual output you see, but just which one has a higher output than the other one. And so if you can do that, either of those two tasks with a set of features, there's a very good chance that the machine learning algorithm will be able to actually create good regression predictions from those same features. So humans are admittedly very bad at that. The other thing we're really bad at is imbalanced data. We get really bored if we see the same thing again and again of a single class. So there are sort of human factors here you have to account for. But modulo those two things, which are two examples that I mentioned in the notes, we're pretty good at this, actually. Our brains have evolved to be very, very good at pattern matching, very good at kind of picking out the important things, focusing on the important things. So by all means, spend the time and actually try to try to do it. If you have regression, yeah, set up two different problems: a ranking problem or a threshold-based problem. You had a question also.
Initially, I wasn't able to understand the intuition for why you're asking us to do this.
Okay.
I think you'll ask it.
Okay. Yeah. So this is very so. Maybe I'll get to later what you do. This is sort of step one, right? This is sort of step one, seeing if you can solve the problem or not. We'll get to what you do in both cases afterwards. So what happens if you can't solve it, and what happens if you can solve it? Yeah. Yeah. So the question that comes up now is which is a great question. It says, what if the actual underlying function is just this really complex thing that you just, I know an algorithm could do it with linear combination, but there's just no way a human could actually do it. There are cases like that, and chances are you do not have one of those. They are very, very rare. You almost always can engineer some feature, can find some combination of features, or can just visualize what the things look like in a way that lets you actually form some reasonable prediction. If you genuinely can't, if your function is literally like a large polynomial trying to find, then okay, that won't happen in data science, I'll say. There's another thing I'll mention in a second that also won't happen, but they are possibilities. They are theoretical possibilities, and they never happen in practice. Okay, I want to give one quick example here that I think highlights this, but also motivates a couple other of my later examples. So maybe this is the wrong place for it, but I'll just mention it here. This is a task that I've worked on similar tasks a lot, and I think it kind of gives a good intuition of some of the problems you encounter, and also how you fix some of these problems moving forward. So an example that I want to think about is what I'm calling a predictive maintenance task. So the idea is you run some factory or something like that, or your client runs some factory. You're a data science consultant. Your client runs some factory, and they want to know which of their machines is going to fail within the next 90 days. Okay, that's a pretty reasonable thing. If they can do that, then they can, send a maintenance crew ahead of time to fix it ahead of time, prevent it from ever having any downtime, and they operate much more efficiently. So there's clear economic value in figuring out what machines are going to fail and which ones aren't going to fail. And you're given for this task signals of signals monitoring the state of this device over time. So I have two signals here. I won't say what they are. But you have one signal like this that evolves like this. All of a sudden, at that point, it spikes, and then we look at this state. It does not actually have to be the present time, but it can be some time in the past, where maybe I know what's really going to happen in the future. But my interface that I present looks like this. In other words, I don't say what the future is. I just show the signals here. I have another stack where I show what actually happens after this time in my training set. But then I go through each of these cases and I mark, am I going to have a failure or not in all these cases, right? And if you cannot do this very accurately, then the chances are that a machine learning algorithm will not be able to solve the problem either. Again, there could be the case where you have this very, very complex function that's some very high degree polynomial of these different things that makes it possible for an algorithm to get exact perfect classification, whereas you can't. But the chances are, if you can't say whether that's going to fail or not within 90 days after seeing that, the algorithm won't be able to either. And I'm going to use this example not just here, but also in discussing what we do in the case that you fail at this task. So what do you do if you can't actually solve this problem here? But before I get to that, I do want to address this notion of superhuman performance, right? Because we're all sort of taught, I think, when we see machine learning about how great it is, how amazing it is, because it can do these things that humans can't do, right? You can take, for example, those MNIST digits you saw, right? So in the 688 class, one of your homeworks, you used images of written digits. You used just a fully connected, no, you used just linear, you used softmax regression, right? To predict what the digit was given the raw pixels. Now, you could take those pixels and permute them randomly to a point where you would have no idea what digit those images were. And The machine, though, it would be the exact same problem from the machine's perspective, right? The machine would still be able to classify those exactly. And these examples, I think, are extremely misleading in the fact that they do not characterize what actual problems are like. We don't have, randomly scrambled digits, randomly scrambled pixels as our input, and our output being, the digit that was before scrambling. We just don't have those categories. We don't actually see those categories in most real data science problems. And so in reality, the power of machine learning, and really the power of data science, does not come from the fact that we can achieve superhuman performance. Again, you can sometimes. You can make tasks where you're going to get superhuman performance, but they are not realistic tasks, almost always. They just aren't what you actually see. The power of machine learning comes from something very different, I think. It comes from being able to attain the same level of performance, or maybe marginally better level of performance, as an expert can. And I mean an expert here, so someone that really understands the problem domain, which you will become, by the way, as you work through your problem. But machine learning can perform as well as an expert. That may take a long time to classify certain things. And it can do it extremely quickly, right, and scale kind of infinitely well. So we can basically have one algorithm that we train to classify tumors and images. If we can do as well as an expert, that's kind of amazing, because we can go ahead and replace all the really expensive, time-consuming analysis of these images and have a simple machine learning algorithm that can do this. We're not there yet with that example, but that's at least the promise of machine learning. It's much less about superhuman performance and much more about scaling human-level performance to a very, very large scale, and very efficiently and kind of very cheaply. And so, again, I know I'm sounding like a broken record here, but if you can't make good predictions, neither can a machine learning algorithm for the vast, vast majority of cases. OK, so let's talk. So then we kind of come to this point. So you've looked at your problem. You set up your problem as this interface of, here's my data, here's my time series, here's my images, here's my video. You can get as fancy as you want. And you try to predict what the class should be. Now, there are two possibilities, right? Either you succeed at this and you get performance that is of the level that you would really want to be able to recreate in the machine learning system, or you don't succeed at it and you cannot get that level of performance. And so what do you do? So if you fail, you go to step 2A. It's an impossible problem. And I put impossible there in quotes for reasons that'll become obvious immediately. But you go to the next step. And otherwise, you go, it's a feasible problem, what I'm calling, and you go to step 2B. So these are the two cases, and I'll handle each of these separately now. Plus a little outlier at the bottom of having impossibly good performance. So what do you do about impossible problems? So I went through this already, but you built a tool to manually classify examples. You run through a bunch of cases, or had a domain, or even better, had a domain expert run through a bunch of cases through your interface. You've classified all your papers. You add up the totals, and you realize, hey, I'm not doing any better than just random guessing, right? What do you do? Well, very important here. What you do not do is you do not just throw more machine learning algorithms at it. This is very, and I say this kind of, it's sort of tongue-in-cheek here, but this is not an uncommon thing to do. Right? People cannot figure out what to do with the thing. They just say, OK, I'm going to throw a deep network at it now. I'm going to throw boosting at it now. I'm just going to try bigger and badder algorithms until hopefully one of them solves it magically. So do not do that. Instead, you have to change the problem until you can solve it. Right? So never, again, you may get to a point later where you can go back to the original problem once you really understand things and kind of start to get at this thing that seemed impossible. Never start there, though. If the problem is not possible for you, change the problem. Right? And we can change the problem. Remember, machine learning, or at least supervised learning, has two things. Right? It has inputs and it has an output. So when you change the problem, we can change two things. We can change the inputs of the problem, or we can change the outputs of the problem. And both those, by the way, are extremely valid. Yeah? What about making assumptions? I think that gets to changing the outputs. Maybe it gets like filtering data, right? So certain outputs you would relabel because maybe you say, well, this case is just not applicable at all, so I'm going to kind of throw it out or something like that. I think assumptions kind of get at changing the outputs because in the formal sense, this is, by the way, the formal sense of inputs and outputs, right? This is sort of the X vector and the Y label. You want to change one of those. Those are what you can change. Or you can, I guess, change your data too. But mainly, I think of that as sort of changing one of these two things just in a slightly different way. So those are our options, right? You can change the data, or the input data, i.e. change the features, right? Those are our input features. Or we can change the labels on the outputs. All right, so I'm going to pause here because I am sort of going through this very quickly. And by all means, I'm not going to, I'm certainly going to finish too fast if I keep going at this pace. So are there any more questions at this point? Yeah.
So when do you realize you need like a domain expert in something?
Yeah.
Is the iris dataset classifying flowers or something like that?
Sorry, say the second part again?
Like I think the iris dataset.
The iris dataset, yeah.
Classifying flowers.
Yeah.
So, I mean, we don't know anything about that, but when do you know you need to change your input via domain expert?
Yeah. So the question is, when do you kind of bring in a domain expert to the problem? And ideally, really, you should always have a domain expert involved in setting up your problem, right? Because if you don't, chances are you're picking some class that you want to predict, and then you're picking some, random or otherwise set of features that may be able to predict those things, and then you have no real notion of how you map between these two things. I think that, so you kind of, the reality is you always want to have a domain expert kind of involved from the get-go. If you don't have that, if you don't have a botanist you can go to and say, what are the things I need to know about a flower to know what kind of flower it is? The next best thing is to immerse yourself deeply enough in the data to the point where you can answer those questions yourself. So read about flowers, a little bit, not too much, but read about flowers up until the point where you have some notion of what might actually be the right set of features and the right output for each of those features. Maybe I'll get to this a little bit in some of the later slides right now, because this notion of an expert is very important. Again, I would expect machine learning to do a better job at me than classifying just off the bat. If you give me an example, here's the petal width, here's all the other things, the iris data set. I would expect the algorithm to do better than me in it, but I would not expect it to do better than a so-called expert, right? So you either need to become an expert to a certain degree, or you need to bring one in and say, hey, what should I be looking at? Fortunately, you're in an environment right now where there are a whole lot of experts in a whole lot of fields. So take advantage of that, by the way. If you do want to do some data science problem in another area, chances are there's someone at CMU who is a reasonable expert in this area. So by all means, go and chat with them and say, hey, can I solve this problem or not? Yeah.
This might be too broad a question, but stepping back from the, is it possible or impossible to do this problem? Do you have any thoughts on, you have multiple sources of data
Yeah.
that you're trying to bring together, and in your mind, you're like, okay, I'm going to be able to merge all of these, this is
Mm-hmm.
going to work fantastic, and then you start finding like, oh, this data set, you don't have the same data for every item, and
Right. So the question I think is largely about if you have. Sorry, I'm repeating the question for the sake of the video. I think the question is about if sort of a different process of debugging when before I ever get to the point of setting up my problem, I think of all these data sources as being something that I can merge together, but when I actually start merging them, I realize that I have all this data for these examples here, and then these other fields are missing, and then the second data source I have these fields, but these other things are missing. And so I think this is actually this is a little bit separate from the kind of the debugging that I'm talking about here, and it's a little bit more traditional in the sense that you can identify what's wrong pretty easily, right? I can look at my data sources and say, hey, this one doesn't have this feature. This one doesn't have, for these examples, doesn't have this feature for these examples. And you can get some sense of kind of what you might need to do, if anything, to fix that problem or to sort of to find corresponding examples within two separate data sets. I think that Oftentimes, though, the answer to that is that it's not actually possible because you thought a data set was going to be laid out in a certain way, and it just isn't. And there isn't really that much to do there other than go and try to collect more data or try to find different data sources. So the process of finding data sources might be something we get to a little bit here, but that one actually ultimately is a pretty tricky one. Just because there's nothing really I can say methodologically. Maybe there is, but I can't think of anything to say methodologically about how you go about finding new data sources that have data that you hope to have but don't have. Though maybe actually this next slide gets to that a little bit. But we'll talk. Yeah.
So in many cases, it happens that the underlying data that you have itself is kind of not sufficient or lacking
Yes.
features as such.
Mm-hmm.
So how do you identify those cases?
Yeah. Right. So again, I sort of said that you have two choices here, right? You can add features, or you can change the inputs, right? Which may mean adding features, or you can change the outputs. If you cannot solve your problem, I am actually telling you. So the way you know if you cannot solve your problem is that you try to do it. If you are unable to solve your problem given the features that you have, your problem is considered impossible as far as I'm concerned. Again, with quotes. What you do next is one of these two things, which maybe I'll get to now, about how you go about changing your features or changing your problem itself to account for these things. And the features one is honestly the more obvious of these two. So I can always change my features. This is something that I think people typically think of or would like to consider, and maybe it gets to this idea of I'm going to collect more data, or I'm going to somehow change my features, because again, you can't really prove a negative. I cannot prove conclusively that this problem I'm trying to predict is absolutely impossible. There may always be some magic feature. That's why I put impossible in quotes here and not impossible without quotes. There may always be some magic feature I have that enables me to, once I find this, to just, that is my signal. And now all of a sudden, just using maybe that one signal or some combination between that and, it has now enabled all these other signals. Using that one thing, I can all of a sudden now solve my problem, right? That's always kind of this hope. And I think a lot of times when people really want to solve a data science problem, or there's just so much value in solving a problem, they hold on to this hope that there's this magical feature that will actually tell them exactly what they want to know and give them, performance that is far better than anything they're ever seeing currently. So here I will actually, more than anything, I would just sort of urge caution. What you should do is you should certainly think kind of broadly about what is the scope of all sort of data sources that I have that may have some, that I may be able to join with my current data, and which may have some correlation with what I'm trying to predict. So you should think about that. But I'll add two caveats. Oftentimes, if you're doing some applied task and you've collected a bunch of data, and you've thought about it a while, or maybe you're working for some company that's thought about this question a while, and they give you a data dump, and then it doesn't work with the data that it give you. Oftentimes, there's not going to be any sort of silver bullet to fix this problem. There's not going to be a missing feature you have that's just going to fix everything. It is certainly never a bad idea to think about additional features. So you can do that. You can explore the idea of adding more features, ones that hopefully are correlated. But do these two things. First of all, do spot checks. So if you're thinking about adding a new source of information, look at your examples, right? Look at the ones you didn't get right in your test set and say, if I had this additional piece of information here, really you should print out a whole new set of test examples because you shouldn't bias yourself by seeing the answer. But say to yourself, if I had this one additional piece of information, just look at it visually, would I be able to do any better on this example that I previously failed at? Right? So the things that were getting wrong before, given this new feature, this new set of information, is it giving me any information, any additional information? So before you write a scraper, before you go through the whole process of trying to merge some new data set in with your existing data set, pick a few examples that you got wrong, that you were unable to classify correctly, look at this new feature that you're looking for, and just see if it's offering you any additional information. If it is, then by all means go through the effort of integrating that new feature, put it in your pipeline, merge the tables in your database, and then go from there. Chances are, though, for most things you consider, it sounds great as an idea. Oh, we're going to include free text from some other source that's going to tell me everything about this. Most of the time, it does not actually provide the information that you want. And so hopefully you can avoid a lot of unnecessary work of integrating it and merging it all by just doing a quick spot check to see, is there any signal here that I'm missing currently? And secondly, I know I also sound like a broken record in this respect, but talk to the people that are solving this problem. So chances are, a lot of problems you work on are being solved to some extent manually by current domain experts, right? So there are people doing maintenance on machines in industrial plants, right? And they use something to determine what they're going to maintain. Maybe they just wait till they all fail, but when something starts rattling in a certain way, you don't wait for it to explode before you fix it, you just go and fix it. So ask them what they're looking for in order to find those features, to make, or at the very least to make sure you have all the features that are actually relevant. So it's very likely that in your first pass, you may have missed something that is very important. Go back to the domain, check with the experts, say, what do you use to predict these things? And if they use a certain feature and you can see a correlation with that and your data, or what you want to predict, then by all means add it to your set of features. Does that kind of answer your question? I'm not quite sure. No. Does that kind of answer your question? Maybe. It's getting at it. So that's kind of the easy one. Everyone kind of thinks about adding features because it is kind of what we think of doing when we have this notion of, oh, the algorithm should work if only I gave it the right inputs. People think of that as adding features. The one that's a little bit less common, but which I hope to impress upon all of you as a really, really useful thing, is to change the problem, change the outputs. Now, of course, you can make it really easy if you change the problem as much as you want, right? You could make it a very easy problem. You have to change it to an extent that still preserves some character of the problem you actually care about solving behind the scenes. But this is not as hard as it might sound at first. So there's two strategies I want to emphasize here. The first one, which is one that I don't see done very often, but which is incredibly useful, is change your label. Instead of trying to predict the future, instead of trying to predict what machine is going to fail based upon what happened in the future, I don't know if there's any signal that predicts that or not. Change your labels instead to be directly the output that an expert would tell you on that example. Okay, so it's a big difference, and it's subtle, but it's a really important one. So go to your expert and say, I have a flower that has this size petals, that has this, etc. What would you do in this case? Right? Ask them that. Show them a history of these signals evolving on a machine and say, would you go maintain this machine or not? And if they say yes, it does not matter whether or not it really fails. I mean, it should have some correlation there, right? Unless they're doing the job really badly. But the reality is people are often pretty good at what they do. Humans, over time, have built up pretty good skills at doing these things. So don't discount the intuition that experts have. And in doing so, when we do this, now all of a sudden, our problem is guaranteed to be feasible. Precisely because we have an existence proof that these labels are creatable by a human, right? A human has been able to create these outputs from this input. So this goes, from a potentially impossible task if you do this, to a, by definition, feasible task. All right? So this is a really, really important idea here, and one that I don't see sort of, at least not taught that often. Now there are cases, of course, where when you do this, the experts don't know what they're talking about, right? So they actually, you're following their advice, you're saying what they would do, but it turns out there's zero correlation with what they predict and what actually happens. So elections are a great example of this, right? There's all these papers recently, or all these articles recently about how experts, political pundits, have no idea what's actually going to happen, and so they're all just kind of full of blowing hot air. So it could fail, but don't discount human experts. And if all you can do is build a machine learning algorithm that recreates what an expert would do, that's already a good success. And we know we can solve it. Or at least we know it's possible to solve. We don't know if we can solve it yet. That's the next part. And the second thing you can do is also, okay, yeah, question.
Why is it so awkward to say that you cannot do something? Like, why do you not change the problem?
Yeah. So this is actually, I think this gets to this one actually. So the second thing you can do is change your goal from saying that you want to get good performance to saying instead that what I actually want to do is characterize the distribution of uncertainty around my output. So that's the second thing. That's sort of the second strategy you have. I think it's not quite changing the output, but it's changing the desired problem metrics in some sense, right? A great example, well, there's lots of great examples actually. I mean, the electrical demand forecasting we had, right? We sort of looked at what the demand was going to be versus temperature. We saw kind of an obvious correlation, but within a certain temperature, there was still a range of possible consumptions that we just, maybe it's just, I mean, you can add a few things to make that better, but at a certain point, you reach a point where you say, you know, maybe this is just random. You know, we can't predict fundamentally what humans are going to do. Maybe it's genuinely random what's going to happen at this point. And so in that case, my goal is no longer to get kind of quote unquote good performance, right? I don't care about getting 100% accuracy. I don't even care about good sounding numbers, right? If it's 20%, maybe that's actually really good because that actually captures the true uncertainty that there is. Think about trying to quantify the uncertainty, the errors in your predictions given your inputs. And that in and of itself is a very valuable and kind of useful tool. And I think it's often, we attach such a meaning to accuracy numbers, like 90% is good accuracy, whereas 30% is bad accuracy, right? Which is completely meaningless, of course, right? It doesn't matter what the raw number is. What matters is whether or not, I mean, in practice a lot of the times at least, what matters is there an economic value or some sort of practical value to getting the predictions that you're getting, right? So if you were just able to get kind of the marginal probability of the labels, so I have 50% are positive, 50% are negative, and my output is 50% on each side, that probably isn't very good, right? So you want something better than that, but what you want to quantify really is the improvement that you get over predicting kind of the marginal class probabilities. Or in the case of regression, you can have other, predicting the mean, say. What's the improvement you get over that? And in fact, I guess I think I have it in the notes, though they're not here. Really, almost all of statistics actually deals with this problem, not with the problem of making good predictions. I think good predictions kind of became a machine learning thing, right? We sort of got obsessed with high accuracies and really good, low errors, these kind of things, right? Statistics is actually known for a long time that what matters is the analysis of the variance, right? When I make a prediction based upon inputs, how does that change my uncertainty relative to making my prediction based upon no inputs, just the marginal probabilities? Now, this seems like a cop-out because you can never fail at this, right? You can always say, I improved this by 0.1%, and that's the results right there, right? So it doesn't take away from the fact that sometimes you still want to change the problem, but there are many cases where what you actually want to do is just quantify the uncertainty rather than anything more fancy. So those are the two things you can do: changing the output, changing the features, but careful because there isn't very much. There's a limit to how much you can go there. Change the outputs. I really like the formula of saying I'm going to listen to an expert and try to classify based upon those examples, those labels, instead of my future labels or my predicting the future labels. And secondly, they might be inherently stochastic. Allow for that fact and accept it when that is the case. Yeah.
I'm wondering how implementable is the recommendation of changing the outputs. For example, in the example of the maintenance.
Yeah.
Listen to the expert. If we're solving a problem, we have several examples.
Yeah.
We cannot make the expert to give us 1,000 outputs.
Yeah. So, Okay, so the question I think relates to, this is a time-consuming process itself, these labels, right? You can't necessarily get an expert to sort of provide you all these things. So there are sort of tools you can apply there. So you can get people to give you kind of rules of thumb that they use. In fact, I think actually that's going to get to a point later, is that when you start solving these yourselves, rather than kind of having just a bunch of labels, what you actually internalize are some rules of thumb. So they're saying, when this happens, then I will do maintenance. Like when this happens, then I won't do maintenance, right? And what you can do is actually automatically label your examples based upon those rules of thumb, maybe, if you don't want to actually get a label for each individual example. This is still, I mean, now we know there's definitely a classifier that can solve this, right? Because you've actually separated the things. So that there should be a limit there. You want to kind of blend them to a certain degree, but there is a lot of value in kind of starting off at that point where you know you can solve the problem to a certain extent. And then kind of slowly meld back into the one maybe that you want to solve, that you really want to solve over time. You can also do things like, we haven't covered it at all, and I won't cover it at all, but things like active learning, where you sort of try to guess what the expert's going to say, and you only predict a small, you only ask for a small number of labels from an expert in order to kind of do that process without having to have them label your entire universe of samples. Active learning or interactive learning is actually a sort of a label that all these things fall under. Okay, so now we've munged our problem either by hacking it to the point where it's no longer recognizable, or maybe finding a new feature that magically tells us what we should do, or however we want to do it. We've hacked our problem into one that's actually feasible. Or maybe we were lucky and our problem was feasible from the beginning. We just sort of saw immediately, yes, this is clearly a system that's about to fail, and our performance is actually quite good. So how do we deal with this? It's not completely trivial either. So it's good news, right? The problem is you can solve your problem. What do we do now? So obviously you can run your algorithm, your machine learning algorithm, and it can do great, and then you're done, right? Maybe. There's one caveat to that. So you're probably done though. You can solve it. You see what it is. You run your algorithm. It finds some rules that are similar to what you thought should be there too. You're great. Everyone's happy. You have your machine learning algorithm now. But alternatively, you can run it and find it does not work. Right? So you run your algorithm, it still does not work. And you say, well, how come? I could figure this out. How come this sophisticated machine here can't do it? And this is not, by the way, a trivial problem, right? I mean, a lot of tasks are easy for humans that are very hard for computers. This is not a completely unimaginable scenario here. And again, you can try, and this is very common to try, you can try just kind of throwing more algorithms, more methods, more data, whatever at it, and seeing if you can improve performance. And actually here there's a good chance this might work. I think there's very little chance in the other case that running faster algorithms will actually work here. Here it could actually work, but it's still time consuming and relatively slow process, right? Because you're not really addressing the problem, you're just kind of trying everything. I mean, more data is a good thing. More features are sometimes a good thing. Just put it all in it and see if it works. And instead what you want to do is you really want to build diagnostics that characterize what is the problem of your algorithm, what problem is it experiencing, and then this will guide you into what changes you want to make to your machine learning setup in order to actually get the performance that you can get yourself, or ideally actually even better. I mean, once you can get okay performance, there is a good chance that the machine learning will do marginally better than you. I will say that, we are not at the limit of performance of machine learning. It can kind of do better, but if you will fail miserably, it will probably also fail miserably. So there's four things that I sort of have, four diagnostics that I find very useful to run virtually whenever I have a task. Sometimes even, and frankly, sometimes even before I've done the manual labeling. These are useful, but they're very useful after I have some idea about what these things should be doing. And the first is characterizing bias versus variance. So we talked about these, and this is sort of training error versus testing error, or related, sorry, it's not the same. It is related training error versus testing error. So again, I think I mentioned these briefly, though I didn't use these terms that much. Bias is when your algorithm's hypothesis class is too simple and it cannot perform well even on the training set. So you're just completely incapable of achieving the desired sort of separation between your classes, or the desired function from your hypothesis. Variance is the other problem. It's where your hypothesis class is too complex. And so you can do very well on training, but you cannot generalize well on the test set. And so a very good way to differentiate between these two scenarios, because they lead to very different actions you want to take, is you look at training and testing performance. And I think a slightly more sophisticated way is looking at training and testing performance versus something like the number of samples you're giving to your algorithm. So these are two sort of or actually it's one, just two different cases. This is one very, very useful diagnostic to run on a machine learning algorithm. So what this plot is this plot is a plot of the loss the algorithm suffers. I'm talking for now about the actual loss that the algorithm is trying to minimize, because that's what it's trying to minimize. So look at that first before you look at something else. And then I'm showing here varying the number of samples. And the reason this is a good sort of axis to look at here is that this kind of classifies kind of characterizes very nicely sort of where you are in the spectrum of, do I have enough data? Do I not have enough data? Is my hypothesis class too complex, or is it too simple, etc. So let's say I get my plot here, and it looks like this. So again, when you have very little training data, the training error will always be low, right? Because even a very simple function can fit a few examples very well, right? So you'll always have very low training loss. But you probably will have very high test loss, right? Because there's no way that actually corresponds to the thing you really want to solve. If you have, as is often the case, kind of a fixed number of samples, or a fixed size data set, you just decrease this manually, maybe by randomly sampling, to have a lower number of samples that you train on. So what may happen is that, as I increase the number of samples, my training and testing error kind of asymptote to the same level approximately. Testing will always be a little bit higher than training, because training is actually what you're minimizing, with your actual optimization procedure. So it'll usually be a little bit higher here. But they kind of asymptote like this. So that's one possibility here. The other possibility, and so this is clearly kind of bad, because here, even on your training set, you're not able to attain the performance that you want to have for your algorithm. This is a case on the left here of high bias. So my machine learning hypothesis class is too simple, and I'm not able to construct a function that I want to represent, even on the data where I'm giving it the answers, right? It's a good clue that your functional class is just too simple. You should try a more complex function class. What that means in practice, in a data science perspective, is you add more features to the algorithm. You could also try a different algorithm too. You could try, a boosted decision tree instead of a linear regression. But honestly, the first thing you should just try is adding new features. And the reason for this is that you already believe that you can solve this problem. And that probably means, not always, but probably means that you have some intuition about what you are using to solve that problem, right? I look at these signals, and so if this one's higher than this one, then it's usually a failure. If this one's lower than that one, then it's usually not a failure, right? You kind of develop those rules of thumb as you go through this procedure of classifying, the good and the bad examples. Now, what these rules of thumb are, or an expert may tell you similar things, right? These rules of thumb end up being very good features to include in actually trying to build a classifier that works, because we already have an existence proof of this level of performance, right? We already know that we can attain it. And if you can somehow categorize what you are using to attain that level of performance, you should take that thing and add it as a feature to your training set, or all your data set, really. Right? On the other hand, what might happen is this instead. So in this case, your training performance is very good, but your test performance is not very good. And in this case, this is the high variance case. It's the case where your functional class is complex enough to represent a function that gets good performance, right? We know it does because when you tell it the answer, it can perform well. It can recreate those answers. So you have a high But at the same time, you're not getting very good performance on the test set. So this is a high variance case. And the thing you do here is very different. So you did not here want to add more features. I guess there's a slight caveat to that. You probably don't want to add more features, or not just do that. Because remember, machine learning is just going to try to perform well on the training set, right? That's all the algorithms really do, is just minimize error on the training set. If you get good performance there already, adding more features that are going to give you maybe better performance, why would it choose to use those, right? Why not just use the ones it's already using that gets great performance? It doesn't know that it's getting bad performance on the test set there. It just knows that it's doing well on the training set. So here, there's no real value, sort of, at least to a first order approximation. There's no real value in just adding more features. So you want to do other things instead. One of the most common things you could do is add more data, right? We know that in the limit of infinite data, training and test error will always be the same because that's how infinite data works. So you could add more data. Maybe as you add more data, this should sort of creep together. But I want to add a big note of caution. And in fact, this has been a sort of an amazing thing that's happened in machine learning is the huge amounts of available data really have enabled performances that were well beyond what we had previously, kind of in the first maybe 10 years of machine learning, just because we can kind of continue this graph farther and farther to the right here, and we can keep getting better and better performance without worrying about picking the right features or engineering them. We just pick a really high capacity model and we throw a bunch of data at it, and it kind of works really well. Be aware, though, that when I say add more data, we're usually talking about changes in orders of magnitude of data. So to get really better performance, we're talking about 10 times more, 100 times more, 1,000 times more examples than what you currently have to fix a problem like that. Okay, and the reason is that the convergence of these things, the convergence of training and test error to the same part is very slow. It's asymptotic and it's very, very slow. And in practice, these models that you typically use are high enough capacity that if you see this situation with a reasonably complex model, you will require a ton of additional data in order to actually make those two things converge to a point. Okay, so data is great. I would not recommend it as the first choice for most people unless you really want to go that route and really believe that I can take a single deep network and just throw massive amounts of data at it and it'll work well. What I would do instead is the opposite of what you did in the first case, which is remove features, right? So if I have enough features, as we know from polynomials and stuff like that, I can fit any function, right? So if I have as many features as my data points, then I will always have zero loss, assuming they're all independent on my training data. So I kind of want to do the opposite. I want to remove features, right? It's probably what's happening here is that we're kind of relying on some features that are not that indicative of true performance, but some random combination of them. We have this weird polynomial, right, that's going through many different points randomly. Some combination of them are causing us to actually get good performance on the training set and bad performance on the test set. So in that case, what you should do is you should start throwing out features, and you should do this in a way that preserves the character of the features that you find important, right? So you should not throw away the ones that you use internally in your own sort of mental model now that you've built that. Don't throw away those. Keep those ones. But start throwing in features that you just don't think you never really considered when you solve this problem yourself. If you have 1,000 features, you probably don't use all of them. Humans are really bad at that. We can't do that, in fact. You probably use some small handful of them, and you should use those to try to quantify your performance. And so that's sort of, data is always a good thing. I would go this route first. And then if you want to, in fact, start from the very beginning, start with just the features that you use. Get yourself to the high bias situation. Remove enough features until you're at the high bias situation. And then see if you can start adding more relevant features to actually attain good performance. The next two things are actually, this is really kind of actually the critical diagnostic you should always run on machine learning. Probably before, frankly, you have validated whether you can do it yourself, but you can do that kind of in tandem, honestly. Yeah?
Let's say you didn't have a domain expert to tell you which features are important. Could you you use like some sort of grid search or classifier?
Yeah, so certainly things like feature selection actually can work very well. We didn't cover feature selection, but there are some very sort of common techniques, things like greedy forward selection, where you just sort of pick, you look for the feature that's like, helps you the most in terms of prediction, you add that feature, you look for the feature that helps you predict next best in terms of prediction, and you add that one. Decision trees actually do capture an element of greedy search, but they're a little bit different too. But yes, there is an element there to greedy search. So yes, a lot of the algorithms kind of have feature selection kind of built in to a certain extent. So boosting, for example, actually builds in a lot of that because it uses decision trees as its base learner, and so you can do similar things. So there are couple more things that I would also mention. They're much less common. They're often emphasized equally, but they're actually much less common in my experience. So the first one is very, very common. Definitely look at those. These you should look at, but don't focus on too much. So the first one is optimization performance. So there is a chance that you just need to run your algorithm longer, and then everything will solve itself. It's, again, a slim chance, but there is that possibility. To see if that's true, what you want to do is you want to plot the loss of your algorithm over the number of optimization iterations you've been running. So these are things like the number of boosting iterations, number of gradient descent iterations, et cetera. And if it looks like this, you're kind of in luck, right? Because you just, I'm almost there. Just keep running, and maybe I'll hit it, my desired performance, right? So maybe I just had a number of iterations that scikit-learn picked by default at first. I just need to keep running a little bit longer, and everything would work out. I'll tell you that probably not the case. Most off-the-shelf libraries are reasonably tuned such that they will run the number of iterations you need, or a sufficient number that you need in order to actually get good performance on the task. So probably what will happen is it'll look like this, I guess, in the high bias case, or this in the high variance case. So optimizing longer will not help you, but it's good to check to make sure this is in fact the case here, and you aren't lucky and get in this position here. The next thing you can do is consider your task loss versus your or task error versus your task loss. It's actually also somewhat of a common one. It's a little not quite as common as the first, but not quite as useful sometimes. But this is actually a pretty common one. So what may be happening here is that if you look at your actual loss, the loss the algorithm is optimizing, that looks great. Test loss, training loss, they both go down really well. They both get to some desired level. But when you think about the actual, very often, I don't really care about logistic loss as my, ultimate criterion for success. It's not how I feel like I've succeeded at a problem, is have low hinge loss, right? That's not how I think about these things. What happens instead is there's some actual, practical application of these things that you do that measures, the economic value of what happens when I do this, or the impact of some result, right? And these things are not necessarily correlated with each other. They're reasonably good. If you have perfect performance in one, you probably have pretty good performance in the other two, but they don't have to be correlated. And so what might be happening is that your task error might actually be creeping up after a while, even though your training error or your loss but in both training and testing is doing quite well. So plot these as well. One common case here is when you have imbalanced data sets. It's very common for your true cost of different types of misclassification to be very different, yet the naive kind of equal weighted prediction performance looks good on both sets. If I have 1% of all machines fail, I just predict they're never going to fail. That looks like great error, but of course the cost of a failure is very different. So I want to include weights in my machine learning algorithm that actually weight the different things to different degrees. And most machine learning things can do that. And the last thing you can do is, of course, go and get a PhD. And I'm being sarcastic here, but I do want to mention the fact that there's always a possibility that your problem is what we call AI hard. In other words, it is a problem that you are able to solve due to the amazing makeup of the human brain, but which an algorithm cannot solve. There are a lot of tasks in vision, in text, and speech, et cetera, that are, despite the progress, that are still, that there's been recently in machine learning, that are still of this caliber, right? I will go ahead and venture a guess that I did not see any problems of this sort, for example, in the project assignments so far. No one's trying to solve vision as their data science problem, which is a good thing. Or if you are, you're doing it in a very narrow circumstance. So that's definitely a good thing. But you may come across this, right? And in fact, these sometimes are the most interesting problems that there are to actually research, right? We want to solve these problems. We want to think about problems like this. But presuming you don't want to, stop your career path and go live in academics forever, though again, I can't imagine why you wouldn't want to do that. You probably want to go back to adjusting your problem. And so, instead of, for example, using the raw images, which are very hard for a computer maybe to understand, use, some features of the images and see if from those things with parts blurred out or whatever, see if from those things you can still classify the examples. You can still solve the problem with a bunch of simpler examples. If you have free text, for example, can you solve the problem when you replace that free text with a bag of words representation? So if I just tell you the words that are in the text rather than the actual text itself, does that stop you from being able to solve the problem? If it does, then you may be in the regime of an AI hard problem, where the actual context, the actual structure of the text really matters, and you just can't solve it any other way. So those are 4 little diagnostics you can do. Again, this one is sort of a little tongue-in-cheek there. These 3 are a little bit more practical. There are plots you should make of your algorithm's performance when you can't figure out why it could possibly not achieve the performance that you yourself are able to achieve. And it's also helpful for seeing, can you improve upon that marginally? Okay, so I'm almost done here. I want to address one last thing and then give a little summary of these things. And that is this alternative step 1, which is actually just as big a problem, and this is impossibly good performance. So oftentimes, and because I know no one here is going to actually do this and print out the pages of the examples and do the exercise, at least not until you've thoroughly kind of failed at your machine learning problem anyway. Because I know you're actually not going to do that. What may happen instead is that you go to solve your problem, you apply your machine learning algorithm, and it works beautifully. You get 98%. Again, I hate the percentages of accuracy, but I'm just going to throw that out there because people think about good accuracy. You get really high performance, much better than you ever expected, and you're ecstatic because you think somehow this machine learning has solved this problem, and you're able to predict the stock market from Twitter and things like that, which people have claimed to be able to do. As hard as it is, because it's a very nice to sort of relish that success when you have one of these successes, be skeptical of this. Still go through the exercise of trying to solve the problem yourself. Unless, by the way, unless the problem is just so obvious that it's apparent how to do it, and you say, yeah, of course, I can have like 3 rules that do that. That's fine then. The algorithm probably works fine, and you're probably getting good performance. But if the task seems really hard, and somehow the machine learning is doing really well on this, again, on both training and test, on both the training set and the test set, be a little bit skeptical, and still try to solve the problem manually. And if you can't solve the problem, then you have to be extremely skeptical about this, because for problems that you can't, again, the class of problems that you cannot solve, that a machine learning algorithm will just perform amazingly well on, is incredibly small. And the chance of you getting one of those off the bat in your first, or one of your first data science problems, is extremely, extremely low. So don't do that. Don't just sort of say, okay, we're done. Be skeptical. And the reason for this is that the other failure mode for machine learning and for data science is that you have let your algorithm cheat somehow. You've somehow included a feature in your data set that is more or less a deterministic function of the output you're trying to predict. And you didn't realize it. You weren't intending to. But you included this in your features. And so you get this amazing performance by looking at this one feature. You're able to look at this amazing performance, and you think the problem solves. But this feature never should have been there in the first place. It was a mistake to include it. You didn't really know what the labels corresponded to, and you by accident included a feature that just gives you the answer. Right? This happens for a bunch of different reasons. So I've seen companies have historical data. This is in something like a failure, for example. They have historical data, and when there's a failure, they go back and they very helpfully fix the data that happened right up to the point of failure because they knew there was a failure, that they knew it was not reliable, so they're just going to go ahead and replace it with zeros or something like that, because they knew that the readings that they had before were not actually reliable. So they went and they fixed their data. But of course, what this means is that your algorithm is going to look and say, hey, look, if this feature is 0 or whatever value they set it to, then there's always a failure that follows this thing. But of course, in real time, you would never have this, right? This is not an actual feature. You don't have it until after the failure's already happened. This is incredibly common. They think they're sort of being helpful. They're creating data in a way that was not intended for machine learning or prediction. It was intended just for a human to look at the data historically and kind of contextualize it. And so a lot of these things that they've added basically let you look at the future to predict the future. So if that happens, look at your algorithm. Build a decision tree on your classification and see if there's one feature that says, if this is equal to that, then predict this, otherwise predict false. If you have that, maybe it's true. Maybe there really is this one feature that no one ever thought to consider before, but it's probably unlikely. More likely, you've probably cheated in some way. And when I say cheat, I mean you've done something that you will not be able to then instantiate in an actual fielded system, right? Because if you actually are running the system in practice, you can't do that. So I also get very skeptical when I see amazing results in reports, because oftentimes people have inadvertently, but it's a very easy thing to do, included some feature that predicts what the future is going to be, and this doesn't really help you very much from a machine learning standpoint. So that's all I want to say about that. Again, there are much more notes on this on the class webpage now that I'm kind of trying to work on, because I think it's a topic that, while very useful, isn't really talked about too much in a lot of these courses. So I want to provide this little handy summary chart here about what you do. And it really boils down to, again, how well you do on a task and how well machine learning does on a task. So this is how you debug data science, or at least the machine learning component of data science. If you predict well on a task and machine learning predicts well, congratulations. You've figured out how to solve this problem. Be a little skeptical still. I mean, it might be that it's not using. You should still check to make sure it's using what you think you should use. But you can be reasonably confident that what you are doing, as long as you verified that, is a reasonable thing to do. If you predict poorly and machine learning predicts well, be skeptical and see if you're cheating. Right? Analyze what the algorithm does, how it makes its predictions. See if it's using some feature that you shouldn't actually be using. Talk with the people giving the data and say, hey, look, I noticed this great pattern that whenever there's a 0 feature here, I can always inspect and I get 100% performance. And they'll say, no, that's not right. So they'll shoot you down pretty quickly, usually. If you predict well and machine learning predicts poorly, now you're in the domain of feasible problems. You should debug your machine learning algorithm by doing these diagnostics, looking at bias versus variance, looking at your training and test error over time, looking at optimization performance, looking at the loss you care about versus the loss that you're optimizing. And finally, if you predict poorly and the ML predicts poorly, then you have an impossible problem. And impossible, again, is in quotes here, because you need to change your problem to make it one where you actually can solve it. You may eventually be able to come back to this problem originally, but not until you've solved an easier problem. Not until you've worked your way there from an easier problem. So hopefully hopefully provides some useful information for you to take to your projects. Next time in class, I'm going to go through an example of a kind of worked through data science example that I kind of worked through, that I hopefully am going to demonstrate some of these things for. Maybe I'm going to take some shortcuts at times, certainly. But I will try to see how these things come up in practice. And then the next time from that, we're going to talk about data science positions. So for those that are looking for jobs especially, this could be very useful, because what is a data scientist and what does it mean when people advertise a position for data science? And then finally, we'll have our last lecture, which will cover kind of the high-level things that we can just talk about briefly. OK, see everyone next time.